Okay, today we are going to introduce the antiderivative. And so I know I'm not here, so we'll kind of talk through this warm-up activity together. So we're going to first define some notation. We're going to say a function capital F of x is an antiderivative of little f of x if it is true that capital F prime of x is equal to f of x. Okay, so what we're saying is if the derivative of one function is equal to the function, then it is an antiderivative of that function. Okay, this is why I've been getting on some of you about using capital F's instead of lowercase f's. Everything means something in math, so there is no room for choice. You have to write it exactly the way that I told you to write it, because here the capital makes a difference. So, for example, if we have the function f of x equals x squared, let's think first about some derivatives, because that's what we're comfortable with. So what is the derivative of x squared? That's an easy one. We know that f prime of x is equal to 2x. Okay, so let's consider g of x to be x squared plus 3. What is that derivative? Well, g prime of x is going to be the derivative of x squared is 2x. The derivative of 3 is 0 because it's a constant. Okay, so now if we think in reverse, and it is notable that those two functions were different, but their derivatives were the same. We want to write a new function s of x so that it has f prime of x equal to g prime of x and has 2x as its antiderivative. So we could literally write anything. I could say s of x is equal to x squared minus 9. Does it make sense that that one would also have a derivative of 2x because the constant is going to zero out? So the point here to notice is how many different functions have a derivative that is f prime of x equal to 2x. There would be infinitely many. Because that constant is always going to have a derivative of 0, and you could choose literally anything to be that constant. Okay, so this part here is really important. This exhausted group of all functions f prime of x equal to 2x as its derivative, we can write this as f of x equals x squared plus c. That c represents just any arbitrary constant. We saw the first example, c was 0. The second example, c was 3. The example that I created, c was negative 9, but it could be anything. And this is called the general solution to the differential equation, f prime of x equals 2x. Okay, now, if we start putting some other information in there. So number 5 says, find a function such that find a function h of x such that h of negative 3 is equal to 5 and h prime of x equals g prime of x. Well, we already know that g prime of x is the same as what we were working with before. G prime of x is 2x. So we need to choose something that has a derivative of 2x, but this also must be true. So here's how we can think about that. We know that we want h of x to be x squared plus some constant. But now we can use that. It's called an initial condition. H of negative 3 has to equal 5, and we can plug that in. So if I do h of negative 3, that has to be 5, and I need to plug in negative 3. Whoops, I'm thinking ahead of myself. And so we can solve for c that way. So this would be 9. When we subtract from both sides, we get c is equal to negative 4. So that means the function that we want for h of x that meets all of these conditions would be x squared minus 4, because that's the value that we got for c. Okay? So take a moment and think. Remember, we're working in reverse now. We want to determine what the antiderivative of the following expressions would be. So I'd like you to put the video on pause and think about this yourself. We're trying to go backwards. If my function has a derivative of 3x squared, what function must that have come from? So pause the video for just a moment, and then you can check your answers. All right, here are the answers that you should have gotten. Hopefully you took a minute to think about these rather than just fast forwarding, because that's not going to help you understand what you're doing. So for this first one, x cubed plus c, make sure that you have that plus c on every single one, because again, it could have come from x cubed plus 5, or x cubed minus 1, or x cubed plus a half. That plus c matters. The answer is incorrect without it. So you always got to remember to do that plus c. So you can see if we took the derivative here, we'd use the power rule. So we would bring the 3 to the front and multiply and then subtract 1. That's how we would get 3x squared. B and C get a little trickier because it doesn't work out quite as perfectly, the pieces of a puzzle. So you have to think here, I need to multiply by 2. I need to end up with a 5, but I need that 2 in front to cancel out. So that's why you need the divide by 2, 5 halves, to get there, plus c. Same thing here. To get to 2/3, I know that I have to start with x to the 6th. And I know that when I take the derivative, I'm going to multiply, and I'm going to have 6x to the 5th. But I need to figure out a number I can divide by that would reduce down to 2/3. So that's how I get 1/9. The antiderivative of cosine is sine of x, because the derivative of sine is cosine. And then the antiderivative of sine would have to be negative cosine of x, because the derivative of cosine is negative sine. So to make it positive, I need it to be negative. And then f, the derivative of 2x, is 2. But you need the plus c on everything. Okay, let's talk about some notation so we can formalize this a little bit. Okay, so remember we've talked about, this is called a differential equation. dy dx, that's our derivative notation in one form, and that's equal to f prime of x. That basically says the derivative is equal to the derivative. So if we multiply both sides by dx, then we get this. dy, that means the change in y, is equal to f of x, or f prime of x times dx, which is the change in x. We can separate those two things. And so what we do is we use what's called indefinite integration, and that finds the antiderivative of both sides. The indefinite integral is denoted by this integral sign, and notice this is different from what we were doing with the area. There's no numbers on it, and that's why this is called an indefinite integral, because it's not finding area. It's doing an underderivative is what it does. So you take the antiderivative of both sides here, integral. The antiderivative of dy is just y. Basically, this is 1 dy. So if we think of the antiderivative of 1, that would just be 1y. Okay, so that's where that's coming from. And then we don't know what f of x is, so we can't work over here. But the answer is always going to be f prime of x, f of x plus c. So an antiderivative is the inverse operation of a derivative. So the opposite of differentiation is anti-differentiation. They are inverse operations, just like addition and subtraction, multiplication and division, and blah, blah, blah. So here's sort of an easy way to think these through. So there's a set of rules that we're going to apply to find the antiderivative, just like we did with derivatives. So you have to do a lot of memorizing here. The good news is you already know them. They're just backwards. Instead of thinking of the derivative of something, you need to be thinking what's the answer to the derivative. And it's the same rules that you already know. But the power rule gets changed a little bit. If you think about what we've done with the power rule for derivatives, the power rule for derivatives is that if I want to take the derivative with respect to x, of x to the n, we multiply by n, and we subtract 1 from the exponent. So it makes sense that what we want to do is we want to do those things in reverse. So when we're doing the power rule for integrals, the first thing that we do is add 1 to the exponent, because the last thing we did in the derivative was subtract 1 from the exponent. Okay? And then we want to divide by the new exponent. And that's going to get us back to this n right here. Okay? So add 1 and divide by the new exponent. Notice for this rule, n cannot equal -1. So like x to the -1 power, it doesn't work that way for integrals because you would end up with a divide by 0. There's a whole different rule for that we'll get to later. So if we look at number 1, also don't forget plus c on every single one of these. Just like with derivatives, if we have radicals or any other thing with exponents, we have to first convert it to be a power because that's the only rule we've got is the power rule. So for number 1, the antiderivative of 5/2 x to the third. The first thing that we're going to do is kind of keep our 5/2. Just like with derivatives, you can pull the constant. And now we're going to work with the x cubed. So the first thing I do is I add 1 to the exponent. So my exponent is now going to be 4. And then I divide by my new exponent, which was 4. Now we just need to simplify this down. So when we multiply straight across, we're going to get 5x to the 4th over 8 plus c. And that's our antiderivative. For b, we want to rewrite this as x to the 1/2 dx. So again, to start here, we need to start by adding 1 to the exponent. 1/2 plus 1 is 3/2. And then if I divide by 3/2, that means I multiply by the reciprocal 2/3 plus c. That's the answer that you get. Okay. For c and d, we're going to have to change this to negative exponents. We want to think of this as x to the -4th dx so that we can use our power rule. So if we add 1 to the exponent, this time we get x to the -3 divided by -3 plus c. And then for d, we rewrite this as x to the -1/3 power dx. So when we add 1, we get 2/3. And when we divide, we multiply by the reciprocal, so we get 3/2 plus c. Easy. We're just doing the same thing. We're just doing the steps in reverse. Okay, so last thing. Here are all the integration rules that you need to have memorized. But again, notice, and I would still make flashcards for all of these because you got to be able to do them backwards and forwards. But notice, these are just the reverse of what we had before. So for example, we know that the derivative of sine is cosine. That's the rule that we already know. So that means that the antiderivative of cosine is sine. It is also important, worth noting here, these first 5. Okay, these go in step with the derivatives as well. So the integral of 0 is going to be a constant because the derivative of a constant is going to be 0. Problem is we don't know what that constant is, so that's why we just call it c. These two are the ones that I really want to point out to you, is the constant multiplier rule. So just like with derivatives, we can kind of just bring the constant along. With integrals, we can just pull it out and integrate the part that's left and then multiply the answer by k. And then also the sum rule, you can split your integrals apart and integrate piece by piece. So that's good with something if we had like the antiderivative of 3x squared plus x dx. Well, you can just work your way through one at a time. So the first one would be x cubed. The second one would be x squared over 2 plus c. One term at a time. Okay? So you are going to have to memorize those rules. And yes, they do need to be memorized by the time we take our quiz on Tuesday. So spend some time this weekend. Now here's the last thing. Not all of your integrams are going to match a rule exactly. So we have to do some work rewriting the integrand before we can take the derivative sometimes. So for example, there is no product rule and there is no quotient rule for integrals. The processes that you would need to use in those cases are a lot more difficult and a lot more involved, and that's not a technique that we talk about until really Calc 2. So we have other things that we can do instead. So the first thing that we would want to do for the first one is, since there is no product rule, that means I need to multiply this out. So we're going to FOIL this out to make it the integral of 6x squared, let's see, minus 10 plus 9 minus x minus 15 dx. Now that's all power rules. So we can work through there. That's going to be 6x to the third over 3 minus x squared over 2 minus 15x plus c. And I can reduce that to be 2x cubed minus x squared over 2 minus 15x plus c. That's our antiderivative. Okay. For b, this is one where this looks like a quotient. We can't actually do the quotient rule, so that means we need to go ahead and divide this out. So I'm dividing all of these by x to the 1/2, which means we can do each piece divided by x to the 1/2. So x divided by x to the 1/2 is x to the 1/2. This has a power of 1. 1 minus 1/2 is 1/2. And then we get minus 2x to the negative 1/2 for the second one. We've done that with derivatives as well, just divide it out. And from there, use your power rule and dot, dot, dot. I'll put the answers up here at the very end. For c, again, no quotient rule, but we can think about what we know about our identities here. This could be sine of x over cosine squared is cosine times cosine dx. So this piece here, sine over cosine, we know is tangent, and this piece here, 1 over cosine, is secant. So this is the integral of tangent x, secant x dx, also known as secant x tangent x, and we know that that is the derivative of, that is not that one. That's the derivative of secant of x. The derivative of secant is secant tangent. So the integral of secant tangent is secant plus c. So two things that you always have to remember. Always remember that when you set up your integral, the integral of whatever, you must have a dx at the end when you're taking the integral with respect to x. That is the same thing as when we do derivatives and we say we're taking the derivative of y with respect to x. We are integrating this function with respect to x. So don't forget that. That piece has to be there. And then the second thing is that your answer is always going to have a plus c at the end when you're doing an indefinite integral. Okay? So now you can start working on worksheet 2.